Welcome to this semester's course entitled Estimation of Signals and Systems. That is how we have named it here. This course could have been given some other names as well. For example, this course could have been named Statistical Signal Processing. So, they are, so basically we will be talking about estimation of signals and systems. So, before we get into the course, we will let us see what we. So, this is today's lecture is titled Introduction, and what we intend to do is to basically give two things, introductions of two kinds. Firstly, we want to give introduction to the area, a very brief introduction to the area, because many of us may not have had any exposure, prior exposure to estimation. And secondly, to give an introduction to the course. What are we going to cover in this course? What are we not going to cover in this course? How are we going to go about it, etc. And from the next class, we will actually go into the course. So, it is relevant to ask, probably relevant to begin our course. You know, it is always before we, very soon we will get into a thick of mathematics, and so while you are beginning, it is good to take a bird's eye view and ask some rather fundamental questions. So, it is probably relevant to begin from this question: what is estimation? Whenever I have to define something, it is my habit, and I have generally found it rewarding, that you should go to a dictionary. So, yesterday evening, while I was trying to write this, while I was trying to write what is estimation, I checked up a dictionary, and the dictionary mentions two things. I mean, it describes estimation using two phrases. That is what I found. So, it says first it said that it is an approximate calculation. By the way, can you see this clearly? All right. And the second thing it says, it is that it is a kind of judgment based on available evidence. That was very interesting, because it really covers a lot of things which are typically covered under, under estimation theory. You know, people who write dictionaries are really careful about what they are writing, and they really get the meaning out very nicely, especially if you take good dictionaries. So basically estimation is somehow these two. How? So, let's look a bit close on these definitions. First of all, it is judgment. Judgment is a sort of a non-technical word. So, what do we mean by judgment? Actually, we do various kinds of things which can come under judgment. For example, we can do a kind of prediction, we can do detection, that is whether something is there or not, it is a kind of judgment. We can do classification, whether the object that we are seeing, whether it falls in this class or that class. We can try to judge its value, and we can also try to predict something in the future, and all these. So these are actually very well defined, kinds of estimation problems. So when we talk about estimation in this course, we will in various courses of discussion, we will go through these kinds of problems. So we will consider prediction problems, we will consider detection problems. So all these come under estimation theory, and it is judgment based on available evidence. That means that we don't really know it for certain. We try to kind of we try to kind of guess it in a way. It may be an educated guess, but it is guess nevertheless based on incomplete information. That is why it is written as available evidence. So there is some unknown and uncertain element in this process. That is what makes the problem of estimation non-trivial, right. That is why it is so interesting to study it, and that is why people have studied it for more than 100 years and have taken to a very high level of sophistication, as we will, at least some of it we will see in the course. So it is basically, it is a kind of computation which is made in a backdrop of uncertainty. There are certain things which we know, there are certain things which we do not know, and we have to compute, we have to make very good guesses about some other things about which uncertainty exists. This is the basic nature of the problem, right. And naturally, for doing that, I mean, the kinds of computations we are doing, they will become approximate, as we will see. This issue will also come in, because actually whenever we will try to predict something or detect something, we have to create and use what we call models, right. So that is, we have to somehow in some using some mathematical structures, we have to describe or capture a kind of generalized behavior of the object that we are, we have to say that, okay, if I observe this, then I have seen that for the last 1 month I have been observing, and if I observe this, generally with good certainty that is likely to happen. So this is the kind of behavior. So this kind of behavior we will have to capture using mathematical structures which we call models. And it also turns out that real physical phenomena, that we everything in this world is actually a cause and effect thing. So what we are seeing is actually definitely caused by some phenomenon or the other. Only thing is that these phenomena, I mean, some of them are predominant and we will try to explain them. There will be hundreds of other things which will be so which will be so complex, they may be so complex that we will not be able to describe them. They also may not be so important because they will eventually contribute less to the overall phenomenon, right. I mean, I typically give this example, that suppose, and to what level you will model also depends on your purpose. For example, all of us know about digital electronics. You see, suppose when you have already studied about digital electronics. So when you look at a counter, you think that a counter is made of flip flops, and you have a state transition. You know what is the state transition table of flip flops, and you construct the behavior of the counter in terms of the state transition table of the flip flops, and there you stop. Is it not? But just imagine that this flip flop is actually made up of gates. All these gates are actually made up of transistors, and all these transistors are actually nonlinear dynamical systems. That is, if you see a small signal model of a transistor or even a large signal model of a transistor, it is actually a dynamical thing. So you now imagine that if you started modeling that counter from this transistor, or even had gone to holes and electrons, then what would have been the model of the counter? It would have been intractable. You can't do anything about it. You can't handle it, you cannot describe it, you cannot compute, you cannot do anything. So we instead, so we are not finally at the, down, everything is made up of electrons and then maybe etc. So that does not mean that we are going to model everything at the level of electrons, right. So we will model it at a certain abstraction level, and why we will model at that abstraction level? You see, the characteristic of the transistor actually comes out when this counter will be changing states. That is, how fast it changes states, what is its rise time, what is its fall time. Only at that time this particular dynamical behavior will be of interest, if you really want to look at that very closely. But otherwise, in the counter's life cycle, 99% of the time either it is staying at 1 or it is staying at 0, and only 1% of the time it is I mean not even 1%, it is actually much less than 1%, it is changing state. So we can ignore that. Why take so much complexity just to model that? So that may be suitable for your purpose, but remember that the person who actually designs that gate or designs that flip flop, I mean the actual VLSI designer, for him it is that edge which is of paramount importance. So he always tries to, one who designs it always looks at that edge and then sees it as a transistor and then tries to optimize its rise time, etc. So where you will model it depends on your need, right. So here also we will especially I mean random phenomena depends on n number of factors. For example, suppose what is the if an aircraft is moving, then what is the kind of force that the atmosphere is actually exerting on the aircraft. That depends on so many things. That depends on that day's particular weather, it depends on wind, it depends on the aircraft's velocity, and so are you going to model all that? So you will probably not model it. So you will think, so you will actually, that is how does this uncertain thing comes? I mean it comes because you don't want to consider, you don't want to explain some phenomena, and you say that these things are random. So you use the word random because you don't want to explain it for your purpose. Just want to know whether it is in general it goes positive or negative. So you are satisfied at that level. If it so it is on an average it goes positive and negative, its mean is 0. I don't want to explain more than that. So it is for these reasons that these calculations in the strict sense are approximate, because they use certain approximate descriptions of the actual physical reality which takes place, and that is basically the origin of randomness, because certain phenomena are either not explainable or not measurable, or it is not desirable to try to explain or measure them, right. So this must be borne in mind, okay. So next question is estimation of what do you want to estimate? So in this course we are talking about estimation of signals. Why do you want to estimate them? Because they may be unmeasurable, right. For example, unmeasurable feasibly. Sometimes I mean if you really spend a lot of money, many things may be measurable, but I mean we will see some examples where, but it may be unmeasurable for a given application, either because you cannot spend that much of time at that point of time to measure it, or because you don't want to spend that much amount of money. So you treat it as unmeasurable. So it may be unmeasurable or it may be measurable, but estimation is needed typically when things are unmeasurable. Even if they are measurable, they could be noisy. These are some examples where you need to estimate. So actually the signal that you are getting is actually mixed up with another signal which you don't know, or it could be, sometimes it could be that you want to know a signal in the future, so anyway you don't have it, right. So you want to know that what is going to be the stock market value 2 hours later. If you could know it, it will be really fine. I mean if people could predict that, but people can't. If you can really predict that, you will become richer than Bill Gates, but you can't do that. That's because there are, why you can't do that? Because there is a lot of factors. For example, if a government falls tomorrow, it is going to have an effect on the stock market. So there are so many unmodeled factors that it brings so much randomness into the problem that you cannot predict it, right. So you see, randomness directly comes from unmodeled, from factors which are very difficult to model. In this case, social, political, physical, natural, various kinds of phenomena. If you have an earthquake tomorrow in Tokyo, the stock market is going to fall, right. And we are going to typically talk of systems which are dynamic, that is, we are not going to talk of static systems, which are simpler, but we don't have time to. So we will directly go to dynamic systems, which are somewhat complex and maybe single input, single output, various kinds of basically dynamic systems we will consider. And again, so for both signals and systems we will have to, whenever we say estimation, actually we will represent those objects as models and then always pose the estimation problem in terms of that model. So, the model is a paramount thing, right. So, this is what we are going to estimate. Estimation, actually, you know, we are mainly students of control. In terms of control, estimation is gradually gaining a lot of importance, because estimation are of two kinds. You know, there may be something is called online estimation and something is called offline estimation. What do you mean? What is meant by online and offline? Offline means that
after the process is over.
That's right. That is, no, I wouldn't say that. What I say is that suppose you have collected some data, then you have, when you are estimating the model, that is the collection of the data during which the system is functioning and the time at which you are estimating the model, they are actually unrelated. So, you could do that, you could just collect the data today and then probably estimate the model 2 days later. This is offline. Online means when you are estimating the model, the system is working. Maybe you are getting the data one by one as you are estimating the model, the system is working, you are getting data through your channel and you are simultaneously estimating. This is roughly speaking online. There are fine distinctions between terms like online and real time in computer science context, but we will use online and real time here as similar words. Okay. Now, offline estimation, the kinds of algorithms that we will use here mainly we will look at online estimation. So, that is more challenging and more difficult. And now, online estimation is becoming more and more important especially in control applications. Basically, because of the fact that in control yes, because estimation is now becoming an enabling technology. You see, people have generally solved the problem of fixed control more or less well, in the sense that offline getting the model, designing a controller for fixed controller and then letting it work. This problem is being tried for a long time and it has reached some stage, and except for very complicated processes like biological processes which we understand don't yet understand properly, the control problem is reasonably solved. But now what people are trying to do is that they are trying to gain higher and higher level of performance. So, how they are going to do that? So, they want to make, now the modern control systems that they are trying to make, they are trying to make it adaptive. So, it should change according to situations. So, if a ship, suppose you are designing a controller for a ship. Now, what is the main job of the controller for a ship? It is to maintain direction of motion of the ship, right. Now, what is causing problems? Why can't the ship, once it is set, why can't it move that way? Because there are waves which are always causing disturbance. So, and remember that the nature of these waves in a sea can drastically change depending on weather. If you have a calm sea, both amplitude and frequency of the sea waves hitting the ship will be totally different from that which will occur on a choppy day. Which will occur on a choppy sea or during storm. Amplitudes will be more, frequency will also be more. So, a controller which has been designed for this one will not work so well for that one, right. So, this is a typical case where you may like to adapt your controller, and depending on what kind of disturbances you are getting, you may like to use a different controller. That will give you quite good performance, quite better than I mean having a fixed controller for all weather, right. So, this is a typical case where adaptive control is to be used. Similarly, people want to build systems which are autonomous, that is they do not need supervision, they do not need manual intervention, they can work by themselves, right. People talk about intelligent systems, that is systems which can gain information from its environment, assess it, take decisions about, and systems which are fault tolerant. That is, even if something fails, after all it is a machine, even if it fails, it is going to give, maybe performance will degrade, but it will degrade gracefully, it will not suddenly come apart, right. So now after solving the basic problems in control and I mean automation, people are now trying to build systems which have this kind of characteristics, and this kind of characteristic immediately will imply that you must have a system which continuously monitors what is happening in the system and its environment. So it must continuously acquire signals, it must continuously assess whether these signals are okay, and it must classify, compute and find out what is the situation, and then make appropriate decisions, change control strategies. So all these things basically will require two things. One is online system monitoring, so you need a technology for that, and you need a technology for what is known as supervisory control. Actually much of what you will learn in this MTech program here is for a level of control which is called automatic control, right. We have there is just higher to that you have another layer of control which is called supervisory control. I mean typically speaking, you must have, even in your undergraduate you must have learnt about this control loop, that is here you have a controller, here you have a plant, here you have a feedback. This is the typical, so this is C controller, this is plant P, and this we call reference input R. This is plus, this is minus, this is the error E. This is what we know as the control input. Now where does this come from? We do not bother about it generally, but this comes from a very sophisticated, I mean to be able to know when to apply what reference actually requires another level of very sophisticated computation, and this comes from supervisory control. For example, if you take an aircraft example, then they clearly distinguish between these two levels of control. If you say a controller to an aerospace engineer, he will understand this. This is the control loop. If you ask where this comes from, he will say it comes from guidance. There is another loop which decides what command to give to the controller, that is called guidance. So basically guidance is a kind of supervisory control. So you need for achieving these, you need a lot of functions of the supervisory control. For example, changing a controller, now use this controller, now use that controller. Who does that? That has to be done at the supervisory level, right. So basically this online estimation, you can think that it is like a just like a sensor, just like here it is a sensor which gives a feedback to the automatic controller. You can say that the online estimator just acts like a sensor for the supervisory control. After all, a sensor gives the information which it needs. So all the supervisory control information are provided by an online estimator to the supervisory controller, which can accordingly give set points to the automatic controller, right. So I am just trying to explain that in a typical control situation, where does this estimation come? So having seen so many abstract things, let's see some concrete examples, right. Concrete examples of application. For example, we have we have already talked about guidance. So, you have seen during the during wars that one missile is going, another missile hits it. So, the missile has a controller. Who tells it where to go, which way to turn? That comes from guidance. How does the guidance decide to I mean what should be the turning? It knows its own position and it tracks the target. There is another missile which it wants to hit, so it tracks the target. So how does it track the target? It tries to get it tries to estimate the position, velocity, acceleration of the target. So it says that okay, if this is the position, velocity, acceleration of the target, then after 0.1 second it is going to be there. So now I am oriented like this, I should turn like this. So you need estimation, right? That is why target tracking. For example, in manufacturing, when you are doing very precision manufacturing, the quality of manufacturing depends on the condition of the tool, how sharp it is, whether it is gone blunt. If it has gone blunt, then you are going to get bad surface finish, you are going to get bad dimensional accuracy. Now the point is that every 1 hour, if you have to stop the machine, open the tool, take it to a microscope, measure its dimensions, that is not feasible. Then you are going to interrupt production like anything. So can you monitor the condition of the tool online, maybe by putting a force sensor on the tool, which will sense what is the cutting force in the y direction. So from there, can you estimate? So you are actually looking at the cutting force and you are trying to estimate what are the dimensions of the tool without measuring it, right? And you are trying to judge whether the tool needs to be changed. So you are judging based on available evidence, right? So for example, you have speech processing. So I am speaking now. For example, nowadays people are going. I mean, I was rather surprised to find that in the United States, if you go into the bank too many times, you are going to be charged. They will cut money from your account, because their logic is that if we would like to give very good service to my customers, and if too many customers are coming to my office, then I need to have a bigger office. I need to have bigger staff. So by coming to the bank too many times, you are actually putting financial pressure on me. So you should pay. But you can do all business without coming to the bank. For example, if you want to know your bank account, you want to do something, you can do everything, and you can do it over phone. So over phone you can ask for your bank account balance. Now point is that anybody can do that. Anybody should not be told what is your bank account balance. So the system will have to recognize who is speaking, whether it is the account holder speaking or whether it is somebody else speaking. So how will the system know? So the system has to model your speech and estimate some parameters of your model and then store that. So when you are speaking online into your bank server, it will take the speech signal, it will extract parameters, it will estimate whether it matches with those stored coefficients, and then it will allow you to know whether what is the balance in a given account. This requires estimation, right? So this is speech processing. In fact, in speech processing, nobody speech signals, image signals, they are very dense samples and they take a lot of bandwidth for communication. So generally when they are transmitted, nobody transmits the signal value sample by sample. Actually what they transmit is a set of model coefficients, which are, so you estimate the model at this end, send only the model coefficients to the other end, and then reconstruct the signal using that model at the other end. You do not send the actual speech signal sample by sample. That will take too much of network bandwidth, right? So you have speech processing. There is huge application in communication. One of the biggest applications of estimation is in communication. Various kinds of problem, noise cancellation, channel equalization. Noise cancellation, have you seen that there is an area called active noise cancellation. That is, you create a noise which will be in antiphase with the other noise which you want to kill. So if you can predict that my next noise sample is going to be minus 1.5 volt. So, you create a noise which is going to be plus 1.5 volt, and they will cancel because it is wave. So, there is going to be destructive interference and the noise will go. This is called active noise cancellation. Now, if you want to do that, then you have to predict what is the next noise sample going to be. How are you going to do that? You do not have the sample in your hand. You are going to in advance produce a sample which with very good probability is going to cancel the sample which is actually going to occur. That requires estimation, right. So, it is for these kind of, so it comes from a large number of wide areas, from communication to manufacturing, and all advanced applications are now starting to use estimation. So, this, I mean, I think our subject is going to be pretty interesting, and we will also try to put in some application bit, though this subject is somewhat mathematical and theoretical in nature, but we will see, right. We have 10 minutes time. So, let us quickly take a look at the course organization, right. May not make too much sense to you right now. Before that, let me discuss what is what I call the course flavor, that is the broad things which I thought should be there. First of all, we are going to talk about a stochastic treatment. Stochastic means probability theoretic, random. There is a, that is, it will use probability theoretic methods. There are other methods also. We are going to stick to them. Typically, we will direct our study towards linear dynamic models because they are simpler. And what I mean by limited breadth first exposition is that I am not going to take one problem, let us say Kalman filtering, and then go deep into Kalman filtering. I think as a first level course, it is good to know that the basic principle of estimation, how they can be used in a number of applications, right. So, we are going to take a breadth first exposition. We will cover each to certain depths. Okay. We are not going to go too deep into any one of them, because there are various kinds of applications. It turns out that actually there are some fundamental concepts. For example, maximum likelihood estimation, that is a concept that can be applied to various kinds of problems. So, it is good to first of all know what is the concept itself without getting, I mean, without always learning it in a given context, because then you, I mean, tend to think that that method is actually only applicable for that problem. That is not the case. A method can be applied for many problems. Okay. So, we will try to have these application independent fundamental concept of estimation separately distilled out, and then show that how in given context they can be applied. That is going to be our approach. And we will always, I feel that at this level you should always keep one feet on the ground, even if the other feet is not on the ground, at least one should be on the ground, otherwise you have a tendency to fall. Okay. So, we will always attempt to relate to physical domain problems solving. So, we will solve numerically, we will try to do assignments, we will try to write codes. Actually, in this subject, unless you write some code, this subject is highly numerical. So, unless you get a feel of the numbers, you do not really get a feel of the method. So, it is very nice and to code some of these methods and actually run them, and then feed them with various kinds of noise and see how it actually performs, what it is really doing. That gives you a different kind of feel which theoretical notations do not give you. So, we are going to also try to do that. Okay. So, now let us look at the course organization. Initially, we will review probability theory, and we'll more or less this will do a bit fast, although we will start from fairly basics. So, you have to read this up. Okay. And then we will come to stochastic processes. This is our main object of study. We want to study this, but to come to that we will have to first review some concepts of random variables. Before that we cannot really discuss this. So, then we will come to stochastic processes. This gives me the basic mathematical tool of looking at the problems which are supposed to be handled in estimation. I will give you you do not have to copy it from the screen, because I will give you all these notes. So, there is no need to try to desperately copy from the screen, you cannot, there is too much material here. Okay. Then after having learned about the basic concepts of estimation, we will the basic properties of random variables, we will see some basic concepts of estimation, basic approaches. For example, the Bayesian approach, what does it mean, what does it say, how does it try to use available information before trying to solve a problem. Okay, that's the hallmark of the Bayesian approach, that it says what do you know about it anyway. So try to use that to get better estimates, right. So it's actually a philosophy. So we will have to look at that. Then we will look at two basic kinds of estimators called maximum likelihood and maximum a posteriori estimators. They are also, I mean, approaches which can be applied to various areas. Then we will look at what is known as the least square and the minimum mean square estimates, mean square error estimators. They are very convenient, widely used. Then we will have to look at various properties, that how do you know whether an estimator is working fine, what are its performance characteristics. So you have to know of various things like bias, variance, mean square error, consistency, efficiency. So there are certain basic properties which will apply to any stochastic estimator. So we will see what they are, how they are to be evaluated, right. So by doing this, we will learn the some of the fundamental concepts in an application independent way first. Okay. Then we will come to estimation of signals with linear dynamic models. So again, the model is very important, and so we will see estimation in two kinds of models. For example, we will see if you see the signal processing literature, then you find that they will always begin initially with input output models, FIR filters, IIR filters. That is the way they learn signal processing, right. So we will also learn it that way initially, because input output models are simpler. So we will learn what is the optimal estimation and prediction with linear filters. There are very nice simple results available which tell you that what you could achieve, what is the best that you could achieve theoretically speaking. So we will see what is best achievable, and then we will see that obviously we will not be able to achieve that. Why? Because it will require certain, I mean, knowledge of certain things which we will not have in practice. So it will say that, do you know the covariance matrix of that quantity? If you know it, then you can construct an optimal estimator, but we will not know it in practice. So under the given limitations, what we can do so that we can reach very good suboptimal performance, and how we can keep on learning more with the data, adapting our filters so that we gradually approach the optimal performance, that we have to study, because that is a practical approach. This is a theoretical result. This says that this is the bound, this is the best that you can do, and this is how you can practically try to achieve that best, come closer and closer, and then we will see some applications, and then we will come to the state space model, and then basically look at the celebrated Kalman filter. Okay. So we will see the Kalman filter, its basic derivation, what are its basic properties, orthogonal properties, etc. We will see how to compute it, and we will see some extensions again, because the basic Kalman filter will have to be stretched in various directions to take care of realistic situations. So you have extended Kalman filters, adaptive Kalman filters. So we will see some extensions which are required. Then again we will see some application. So this says basically covers signal estimation, right, and then we will study an area called system identification. We said estimation of signals and systems. So now the signal part is over, now we are talking about system identification, which means that how to get the model of a system. So obviously to get the model of a system, you have to apply some inputs, get some outputs, and then see what is the relationship between the input and the output, and then try to compute that relationship. So that is called system identification. So we will again see basic concepts. There are two kinds of models. There are some models which are called non-parametric, and there are some models which are called parametric. Okay. So we will briefly see non-parametric methods. Non-parametric methods are not so much important because they are not so much useful. What is more useful is the parametric methods. So basically parametric methods assume that there is already a structure, For example, second order, you can assume that this system is going to be a second order system, second order transfer function. Then you find out what is going to be A0, A1, A2, B0, B1, B2. So the structure is assumed and you only want to estimate the parameters in that structure. Okay. This is what people usually do. So what kind of model structures can be used, and there are some most widely used algorithms: recursive least square, orthogonalized projection, extended and generalized least square, which are used for other kinds of noise models, and instrumental variables, which is a very useful approach. And then finally convergence and practical issues. After all, you want that finally the model parameters, if it always keeps on changing, then you are in trouble. So it finally should converge to some value which you can use later. So under what conditions does it converge, and to make it converge in a practical situation, what are the precautions that you should take? So we will see them and then finally see an application. So this is the basic body of our course. We possibly will be left with a few lectures, so I have not formalized this part in the sense this we will have to cover. But what is left, we'll fill up with different other kinds of estimation problems. For example, there are various very nice classification problems. Then there are which are especially used widely in image processing, in areas like robotics. That is, how does an autonomous moving robot, after getting into a room or looking at a situation, how does it understand whether what kind of situation exists, what it should do, what mode it should work. So that is basically a scene classification problem, right. So you can have various kinds of things like classification, you can have fault detection, you can have a problem of sensor fusion. That is if you say, suppose you are trying to get the motion of an aircraft. Now if you use one radar, what kind of accuracy you will get? If you get two radars, will you get a better accuracy of its real position? So it generally turns out that if you use multiple number of sensors, you can actually construct a better estimate. So what are the things related to that? These are highly practical things, and people do it. So depending on the kind of time that we have, we will try to take a look at some of them. So this is our plan in this semester, right? Any questions? Sometimes I tend to go a little fast. For example, I think today I have spoken rather fast because if you have any difficulty, just don't bother about this paraphernalia. If you are the most important person. So if you have a difficulty, you are going to raise your hand and say, I didn't understand this. Please repeat. No problem. Don't be intimidated by these things. Okay. This is a normal class. So our next class is on tomorrow at 4th hour, not 3rd hour.